Now we're going to look at an LC circuit. In the RC/RL circuits, we get an exponential function of t increasing or decreasing to some steady state. When a circuit contains both an inductor L and a capacitor C, containing an ideal resistanceless inductor and a capacitor, first we charge the capacitor to a potential difference Vm. So we're going to assume we've charged that already. There's pluses on this side, minus on this side. When we throw the switch, these are all going to start to move through here. Now, you know, as they start to move, this will try and resist it, but eventually the magnetic field built up. As soon as it's starting to slow down, the magnetic field will then begin to collapse. As it collapses, it will continue to push these charges through due to Lenz's law, till we end up negative charge on that side and a positive charge on that side. Then, of course, you're going to have the same situation. Now the capacitor is feeling a potential difference now, and it'll start running these back through. Now, eventually, when they start to come through initially, this is going to show a voltage opposing it, but that will quickly be overcome, and a magnetic field will develop in here, and eventually it will collapse. Once this starts to run out, it'll see that there's a reduction in current. Because there's a reduction in the current due to Lenz's law, it'll want to keep the flux going, so it'll then carry on pushing these charges through, and we end up back to where we started. So that's a complete cycle, and that will just continue, assuming there's no resistance in the circuit. You know, if that was a superconductor, that might go on for a long time until, you know, well, in principle could go on indefinitely, but in reality, in real circuits, there's some resistance in the wires. I'll just read that through. The process now repeats itself in the reverse direction. In the absence of energy losses, the charges on the capacitor surge back and forth indefinitely. This process is called an electrical oscillation. From the energy standpoint, the oscillations of an electrical circuit consists of a transfer of energy back and forth from the electric field of the capacitor to the magnetic field of the inductor. The total energy associated with the circuit then remains constant. This is analogous to the transfer of energy in an oscillating mechanical system from kinetic to potential and vice versa, with total energy remaining constant. These results can be derived directly from an analysis of the LC circuit as follows. What we'll say here is we will use the fact that all voltages in a loop add to zero, as we have. Here we can say that the voltage across the inductor plus the voltage across the capacitor at all times will equal zero. So we sum up the voltages there. From that step, we can just replace what we know that the voltage drop across an inductor is L di by dt, and across the capacitor is Q over C. What we're going to do now is differentiate that again. You'll see why we do this. With this term, Q over C, remember that dQ by dt equals I, so we can just as easily write that Q equals I dt. So if we put that in there, then obviously when we differentiate both sides, obviously the dt's are going to cancel, and we end up with I over C. So now we've got this, we can rearrange it a bit, and we end up with a second order differential equation, and we've got I isolated on this side. What we'll do is we'll guess some answers for this. The obvious thing to think about here is you want to be able to find a function I that when we differentiated it twice, it gets back the function we started with. Now the obvious one to think about is when you differentiate a sine, you get a cosine, and when you differentiate a cosine, you get a sine back. So sine is a really good one to choose. So we'll guess a solution, and we'll guess it to be this. I equals I naught sine Wt add a phase shift, and we can check that that's going to work. We differentiate this, we get di by dt. Obviously the W comes outside. We get Wi naught cosine Wt add theta. Differentiate it again, then obviously cosine goes to a minus sine, and we bring the W out again. So this time we get minus W squared I naught again sine Wt add phi. So we can see that that works because this function here, I naught sine Wt, is the same as the one we started with. The only difference is this coefficient. Now this coefficient, if it's the same as that, then we've got a solution, yeah? So this works if minus W2 is the same as this coefficient. So the viable solution then obviously is I naught sine Wt add theta, where omega, the angular frequency, equals 1 over the square root of LC. So that obviously is going to work. We've got a function now, this one here, which is going to be useful for an LC circuit. So we can always use this function here to describe an oscillating LC circuit. The angular frequency W then we know that it depends on the inductance and the capacitor, and it's an inverse relationship. So what's interesting about that, if L times C, for example, is very large, then this frequency is going to be a very slow oscillation. If L times C is a very, very small value, then obviously we're going to get a very quick oscillation, so that it's going to be a very high frequency. You can also just reason that out quite obviously, because remember that if you've got high induction, it means there's an opposition, so it takes longer for it to build up the magnetic field. And with C, when C is very large, you've basically got larger plates, so it takes longer for the charges to fill up the plates. And vice versa, if you've got a very small C, then the time it takes to charge up a very small plated capacitor is very quick. And again, a very, very small L means there's very little inductance. The energy gets stored really, really quickly, and then the current starts to flow much faster, because it only takes a very short time to get over that initial back EMF, if you like. So that all makes sense. We've got a nice solution here. We've got a function that describes the LC circuit, plus we've got this frequency term, which nicely tells us the different values of L and C, what the frequency is going to be. That covers an LC circuit.